Hello everyone, welcome back to class. I wish we were doing things a little bit differently than what the process is now, but we will try this and see how it works. We'll continue on with lecture today in regard to Thevenin circuits and Norton circuits out of chapter 9. But first let's go over some issues about how we'll be addressing this class for the rest of the semester. So hang in there with me and let's try to get through this. First of all, make sure you email me with any questions that you may have in regard to the course material or anything else related to this class. That is the best way to get a hold of me, is just to use the OSU email. And that is also how I will typically be in contact with you. Turn all your assignments into Canvas, starting this Wednesday with the assignment that is due out of Chapter 9. There will be a drop box created on Canvas for you to drop all of your assignments in. These lectures will be posted for 24 hours. I've thought very heavily about this. My concern is that the temptation would be to wait till a day before exam and then try to watch a bunch of lectures and get homework done. So I want to post lectures on the day that the class should be held, and the lectures will be posted for 48 hours on Canvas. Every lecture will have a quiz question or questions. They will be embedded in the lecture. This is mean on my part, but it's to help ensure that everybody indeed does participate in watching the lectures. For those quizzes, just submit those answers to my email. I'll give you a little bit more information when we do the first quiz that will happen today. The quizzes can happen anytime in the lecture. It could be in the middle of the lecture, the beginning, or the end. Again, my intention is to embed these quizzes in such a way that you would be encouraged to watch the lectures. Attendance will be taken from the quiz answers, and for each lecture through Canvas. I do receive notification in Canvas whenever you watch the lecture, so just be aware. I know if you're watching the lectures or not. Exam 3 is scheduled for April 3rd, which is Friday of next week. We are going to maintain that schedule. The exam will be timed for 1 hour, and we'll start at 10:30 a.m. on Friday, April the 3rd, just like when our normal class time would be. And it will be given through Canvas, and you'll have access to the exam for 1 hour. There will be a standard 50-minute exam, but I'll go ahead and give you an hour. The exam will be open book. But let me warn you, if you rely on the book for your answers for the exam, other than just maybe referencing one or two items quickly, you will not be successful in finishing the exam. All future lectures, my plan is to post them at normal exam time or normal class time. In other words, the lecture for Wednesday will be posted at 10:30 in the morning and will be available for the following 48 hours. Again, if you have any questions about these items, make sure to email me. Okay, I have a few more notes to discuss here. Let's talk about labs. You know, labs per university policy say that they still must be performed. So, just as we discussed in class Friday before spring break, do all the remainder labs using Multisim. Multisim can be downloaded through Seat IT. Don't go through OSU IT. If you do, you won't find it. Multisim is found in the Seat IT software download page under National Instruments software. Some of you owe me makeup labs. We need to come up with a way to make it fair for the class as a whole. So if you can help me come up with some ideas as to how to do makeup labs, if the class worked the lab in lab using the equipment, it seems to me to be unfair to do makeups by using a multi-sim approach. So help me think through this. Maybe a couple of you can come up with some ideas. Email me as to how we can handle the remainder of the makeup labs that need to be performed. You are welcome to perform the full labs, but it must be done at home. I wish I could invite you to come to campus to go to the lab room and perform your labs, but the university has announced that the campus is completely closed off to students. I don't know how well that will work, but that is the university policy as it stands right now. Of news, we are having discussions in the EET program. Most of our classes are already offered as a hybrid model, in class and online at the same time. It's just in the past that we have not offered the freshman and sophomore level classes in the EET program online. I believe next year there will be a change. Right now we are in the process of having some online sections added so that all 11,000 and 2,000 level EET courses will also be online starting in the fall. So it will be possible to do EET, or that is our wishes or our plans, starting next fall completely online. If you want a face-to-face conference with me, you can ask for Zoom or Microsoft Conference. I've got the hardware set up in my office so that we can do face-to-face via the computer. Again, if you have any questions about any of these points, make sure to contact me via email, and we'll go from there. But I cannot invite you to campus for a face-to-face meeting. Any face-to-face contact in real life has to be initiated by you. Otherwise, let's continue on with Thevenin and Norton circuits. So here we are. We have a circuit. We've got a number of resistors connected to a 12-volt source, and I say this resistor right here, highlighted in blue circled, is the component of interest, and we want to do a Thevenin and a Norton analysis of this circuit. Just to remind ourselves, when we talk about a Thevenin analysis, we are looking for an open circuit voltage. When we're doing a Norton analysis, we are looking, if I could spell, looking for a short circuit current. So let's do the first step here. Let's do a Thevenin analysis of this circuit. And so if we're going to do a Thevenin analysis, then the first step we're going to do is we're going to take that component of interest and remove it, and ask the question, if we leave that gap, What is the voltage there? There's not a component there, but there's an open space there, and we can definitely have a voltage across an opening. So we call that voltage the open circuit voltage. Or the Thevenin voltage. Yeah, they both mean the same thing as far as we're concerned with this Thevenin analysis. So if we're going to do a Thevenin analysis, what are the steps to take? Well, since I am looking for a voltage, I'm going to sum the currents. How do we sum currents? Well, we do nodal analysis. So let's identify our nodes here. So there we are. I've defined or found at least 4 nodes that are necessary. We've got wires connecting here, wires connecting there. Here's a connecting point for wires, and here's another one. So we have 4 nodes in this circuit. So I've created our circles, and I'm going to give the circles a name. I'll call that voltage 1, voltage 2, voltage 3, and this one here I'll call the 0 volt node. That is one of the options, or one of the steps actually in doing nodal analysis, is that we always have a 0 volt node. So now that leaves us with 3 nodes with unknown voltages, and to find those voltages we will sum currents. So let's look at node 1. We want to sum currents for node 1. Well, we note that we've got a wire here, and a wire there connected to that node. So that means I would expect to have 3 terms in the equation that we're summing up, 1 term for each wire. So let's look at this wire here first. Starting from this node, I'm going to work my way to the next node, which is down here. And how we define the current in that wire from this node to this node is we take all the voltages starting with V1 and we subtract any voltages along that path to this node. So we have V1, we're going to subtract that voltage, which is 12, and then we subtract the voltage of the next node. Now we happen to know the voltage of this next node, and that's 0. And then we divide those voltages by any resistance we see on that wire from this node to this node. I see I have 1 resistor, and it's simply 2 ohms. So this is the first term for this first wire of this first node. Now let's do the second wire. I'm going to add that term, starting with that node, working to the next node. We have V1, subtract any voltage on the wire. Well, we don't have any wire on the voltage, so we just subtract the voltage of the next node, divide it by any resistance we see on that wire, and I see we have a 3 ohm resistance. Then we're going to add the third wire here to the right, from this node to the next node. So we have V1 minus that next node, which is V2, divide by any resistance that we see on that wire, and it looks like we simply have a 5 ohm resistance. So now we have our 3 terms, 1 for each wire. All those currents will sum up to be 0. So let's use our advanced algebra skills that we learned in high school, hopefully. And let's collect our like terms. So I'll start off with the V1 term. we've got a V1 over 2, so we'll add that term, so that takes care of that one. Then we have a V1 over 3, and then a V1 over 5. Then we have a V2 term. I need to make sure I include the negative sign in front of that one, and that's simply over 5. And that's the only V2 term we have. Then we have this constant, a minus 12 over 2. We've got a 0 over 2, we won't worry about that one, or this 0 over 3. And that takes care of our V1s, 1, 2, 3, 1, 2, 3, our V2 term right there, and our one single constant. All those currents, again, sum up to 0. So now I want to use my calculator, just because I don't want to risk doing numbers in my head, and get these terms all added together. And this becomes V1 times 1.033 minus V2, and that should be a 0.2. Just to make sure, yep, 0.2. And I'm going to go ahead and move this term over. I have a minus 12 over 2, which is a minus 6. And now I'll just go ahead and carry that over here. And that'll become a positive 6 value. So this is our first equation. So I will make note of that. Then we'll start our second set of equations for the V2 node. So we're going to sum the currents for V2. Well, so that's that node right there. We have 1, 2, 3, 4 wires connected to that node, so I would look for 4 terms if necessary. But I'll start here to the left. Starting with V2, we'll work to the next node. So we have V2 minus V1 divided by that 5 ohm resistor. That's that first wire. Then we got the wire going down. Add that wire in. That's V2 minus the next node, which is 0, divided by that 6 ohms. Then we got this wire here, but I should notice that since we have a gap in this wire, there is no current in that wire. So even though we have this wire connected to that node, we should be able to identify, oh, this wire has no current. So I'm just not going to worry about that wire and just jump up here to the next wire. And so we got this term here with this wire starting at V2 going to this node, which is now V3. So we have V2 minus V3 over any resistances on that wire. We have here a 7 ohm. My penmanship wasn't too great. That's supposed to be a 7. And then we have a 6 ohm, which is a total of 13 ohms. So we have 1, 2, 3 wires with current in them. So we should have 3 terms. We've got the one to the left, the one going down, and the wire to the right. And all those currents, according to Mr. Kirchhoff, add up to 0. So again, let's collect all of our like terms. Since I started with V1 up here, I'm going to make sure I start with V1 down here first. And here it's a minus, so we have minus V1, and it's over 5. And that is our only V1 term. Then I'll go to the V2 term. That's the one that's next. In this case, it's positive now. We have a 1 over 5, and a 1 over 6, and a 1 over 13. So we got 1, 2, 3, 1, 2, 3. So we have all of our V2 terms, and now we've got this V3 term that we need to include also. And so that takes care of our V1s, our V2s, all three of them, and the single V3 term. There are no constants other than this 0, and that just drops off. Again, all those currents equal 0. And so that 1/5 is 0.2. Again, I'm going to quickly use my calculator to make sure I get these numbers correct. And that gives us a 0.4436 minus V3. I have no idea what 1/13 is, but now I do. Looks like 0.07692. All those equal 0. Well, let me move my page up here so we can make sure everybody has a chance to see that. Okay, so that took care of our second unknown node. Now we have one more node to take care of. And so this is our V3 node. We have a wire here, a wire here, and again this wire here, but we should be able to notice now that, oh, this just doesn't have a current in it. Now this just makes V3 on one wire now. So are we okay? And the answer to that is yes, we are still okay. We can still call that a node. That is one of the nice things about nodal analysis. You know, we definitely have to identify the places that are nodes, and then we can add any other place that's convenient to be a node, as long as it's not inside another node. In other words, I could call this corner up here a node if I wanted to, or I could call this corner a node if I wanted to, if there was a reason to do so. But there's no reason to compel me to do that other than we want to know the voltage right here, because we're looking for this open circuit voltage. And that would be the voltage on this side of the dot minus the voltage on this side of the dot. So we need that voltage there and that voltage there. So let's continue on summing up currents to find a voltage. So we started with V1 last time. Well, V1's not there. It's not connected to the V3 node through any other node. We've got a node between here and there, and that node's between there and there. So we just have V3 minus V2 and V3 minus 0 terms to take care of just for that wire there and this wire. So let's go ahead and do that. So we're going to sum the currents for node 3. It looks like my nice blue pen here is about to give out, but we'll see how long it lasts here. So we got V3 going up to V2, so that's V3 minus V2. So we have V3 minus V2 over the sum of those two resistors, so that's 13 ohms. And then we have this going to the left, V3 minus 0 over that 6 ohm resistor. And that's it for that term, and those currents again sum up to 0. And in the bottom space here, I'm going to go ahead and so I have a minus V2 over 13 plus a V3 over 13 and a 6. Again, all those currents sum up to 0. So now I'll go to the next page. And get that third equation assembled here. So, that 1 over 13 term here, minus V2, I already know that is 0.07692 from the previous equation. Then we got our V3 that's got a 13 and a 6, so let me get that taken care of. And that's 0.2436. All those currents equal 0. So now we have those 3 equations. Let's go ahead and put them in our matrix system. We have a V1, a V2, and a V3 term. And hopefully I can squeeze all this in. We have 1.033. We have a minus 0.2. And then there is no V3 term in that first one. And we have a 6 there. The second equation, we have a minus 0.2, a 0.4436, and by golly, I've run out of room here. I wasn't paying attention, so let me switch to something else to write with here. Hopefully this this black pen writes a little bit finer in detail. So we got V1, V2, V3, and 1.033 minus 0.2, 0, minus 0.2, 0.4436, and then that term here is 0.07692. And then for our third equation, we have no V1 term, and this is a minus 0.07692, and this is 0.2436. Okay, so this is supposed to be a to the minus 1. We've got a 6, and then we just have 0 and 0. So we have our system set up. I use an HP prime calculator, so I'm going to go ahead and do everything there on my calculator, and for those of you who may be HP folks, you can follow along, and those of you who are TI folks, hopefully you can follow along with your own calculator, even though it's going to be different than what I do. Okay, so I'll go ahead and go to my matrix system here, and we've got a 1.033, and then we have a 0.2, and I've got a 0 there, and then we have a 0.2 and the negative, a 0.4436, and I believe you guys let me make a error here. This term right here should have a negative sign in front of it, so let's go ahead and make that correction. Perhaps maybe you already caught me in that one, but that should have the negative sign in front of that term right here. Okay, so that is a 0.07692 negative term, then that's a 0, and that's a 0.07692 negative, and then a 0.2436, enter, and then I go back up. seem to have managed to lock up my calculator here. Let me try to get out of that one more time. There we go. Sorry about that. And then we go here to this one, and we've got a 6, a 0, and a 0. Okay, now I should be able to get out of that. And so I have my first matrix there. I'll go ahead and take the inverse of that. And I've got my second matrix, and just do that. And so these are my answers. V1 equals 6.399 volts. V2 is equal to 3.052 volts. And V3 equals 0.963 volts. So hopefully everybody can agree with my answers. If not, maybe you should email me and see if we can figure out what's going on here. So let's go back to our circuit here, and we were looking for this voltage right here. Well, we didn't solve for that one directly, but now we know the voltage up here and we know the voltage down here. So the voltage across this gap is simply this V2 voltage minus the V3 voltage. So our Thevenin voltage, or our open circuit voltage if you prefer, will be V2 minus V3. So that Thevenin voltage equals 3.052 volts minus 0.963 volts. And I actually got a fourth term there if we want to include that, 0.9638. So we have a 3.052 and a 0.9638. Subtract those, and I get a Thevenin voltage value of 2.088 volts. You know, if you come up with something like 2.1, that works for me. So about 2.1 volts is what the Thevenin voltage is, according to our calculations. Okay, so that did the Thevenin portion of the circuit. That took us a little while, but hopefully we were able to follow along. Now, I want to do the Norton Circuit equivalent to that. Okay, so here we go. Back to that circuit. And we've had this portion of the circuit removed. And now we're going to short across those two bubbles and ask the question, okay, what is that Norton current going to be? Or that short circuit current? And so, to get us going here, we're looking for a current. So if we're looking for a current, what tool or method do we usually use? Well, we're most likely going to use mesh analysis. And to do mesh analysis, first of all, we got to draw some circles inside the loops. Again, it doesn't matter which direction I draw these circles, it's just whichever direction I start drawing circles, I need to continue to do so. And by habit, I just do clockwise. You can go anti-clockwise if you want. So there we are. We have 4 circles, and each one of them is a current, so I'll call this one I1. This one we'll call I2. This will be our I3 current, and this will be the I4 current. So we have 4 current loops, and so we're going to have to sum our currents here, or excuse me, find our currents. And we find currents by summing voltages. You know, it seems kind of backwards. We find voltages by summing currents, and we find currents by summing voltages. But let's go ahead and start summing our voltages for that first loop. And according to Mr. Ohm, voltage is I times R. So we got this I1 in this loop here. We're going to multiply it by the sum total of our resistances in that loop. So we have a 2 ohm and a 3 ohm and a 4 ohm. So 2 plus 3 is 5 plus 4 is 9. So we got 9 ohms in that loop. And then we have to ask our question, do any of these other currents touch that loop, therefore affecting any of these components? And the answer to that question, yes. We have the I2 that also goes to this resistance here. And I1 is going down, I2 is going up, so it's working against I1, so we need to subtract that I2 effect through that 3 ohm resistor. And then we have the I3 term, but it doesn't touch the loop. And we have the I4 term, again it does not touch the loop. And then we've got a voltage here. Since we're summing voltages, we better include that voltage. We have a 12 volt supply. I'll follow the arrow here, and it sees the minus sign first, so that's a minus 12. All that equals 0 volts. So get everything collected here nicely. I guess I kind of already did that.